So we're looking here in section 5D, which is just another section on graphics. The difference being in this particular section, though, are the graphics are a bit more complex. So you will see some very more intricate graphs that show you a lot more information than the previous section in section 5C. With that said, however, though, I do believe that the solution key will provide you great insight on several of these graphs. For example, the first one here with this multiple bar graph, I think it's very straightforward as to what's trying to be conveyed, so I'm not going to spend a lot of time here on the first page, or even actually in the first couple of examples, because I believe that by looking at the graph itself that you'll be able to gauge what's trying to be conveyed. And if not, I've got my solution key, and I believe that once you consult the solution key for this section, you'll say, oh yes, I completely get this now. So with that said, the first graph here is a multiple bar graph. Flipping it over to the next page, example 2 is a multiple line graph. Again, I believe that you'll be good with that one. I'm going to move on down though to stack plots. The first one is very straightforward, and I believe that you'll be okay with this one. So this is referred to as a stack plot. But one that might be a little bit more that's actually quite different is the one on the next page, example 4, and that's where I want to focus my attention. To me, this graphic, every time I see it, and this is just one example, if you look at the 5 ABCD lab, you'll see another example as well. But every time I see this particular graph, I always think of that it belongs in a geology textbook. It looks like the cross section of the earth and looking at soils and rocks and things like that. But nevertheless, it is a type of graph that can convey information that we can it's just another way of conveying information, essentially. So this one is looking at the trends in death rates per 100,000 people. So I'm just going to go with the one that has been clearly identified here. In part A, it wants to know what was the death rate for cardiovascular disease in 1980. So cardiovascular disease here is the green wedge. The most common mistake that folks make for these particular graphs is not reading the graph correctly. When you want to read a stack plot that is constructed in this manner, you have to read the top and the bottom of that particular part of the wedge that you're looking at. So since I'm looking at 1980, then I'm looking at the top and bottom there. Just a second, I need to get my pen. Sorry. So the top of my wedge, and I chose this one because it was already clearly marked. They're going ahead and measuring that at 620. I'll be honest with you, whenever I did your homework for this particular section, I actually literally got out a ruler and had to, follow a ruler all the way across to try to be as precise as I could be. Okay, so they're reading the top of that wedge there at 620 and the bottom of the wedge at 180. And again, if you followed it over, you can see it's just a little under that 200, so that makes sense. But how do we find the death rate? We have to utilize these two numbers, and it's very straightforward. Once you know that simple fact that you need to read the top and the bottom of the wedge, you simply now take your 620, the top of that wedge, and subtract the 180. 620 minus 180 will give us 440. So we're looking at 440 deaths per 100,000 people. Sorry. Part B, just commenting on the trends in the graph. We're just looking at, like for example, this blue wedge here is tuberculosis. Since tuberculosis after looks like around 1959, 1960, there isn't any more blue wedge, we could say that then TB has basically been eradicated since 1960, for example. And so you would just comment on each of the other types of diseases. To give you another perspective here, like if I wanted to know what was the death rate for 1900 for TB. So just to add a little something here, just to kind of give you another example. So if I were looking at the death rate for TB in 1900, I would need to read the top and the bottom of that wedge. So here's my bottom portion. Here's my top portion. So I would probably estimate that bottom portion there to be somewhere between 75 or 80, for example, okay? And then the top up here, that's about the halfway mark, so I'd probably estimate it to be 250. So I would say then 250 minus, let's say 80. So if I have 250 minus 80, that gives us 170. So I was looking at 170 deaths per 100,000 people in 1900 for TB, for example. Okay, so just always be sure, as like I said, that's the most common mistake for these stack plots, is not to reach the top and the bottom of the graph. Okay. Just below that are 3D graphics, and these are usually fairly straightforward. This one is in reference to iPod sales um, for um, iPod sales till June 2008, excuse me. Some advantages of 3D graphics: you can visually represent complex data sets, because here you can see multiple years from 2002 to 2008, and then along the top here you're measuring the actual sales themselves. I believe which was were in millions. Yes, it's just above there in millions. And but some disadvantages, unfortunately, of these 3D graphics are that they can be difficult to read. Case in point, if I move down here to letter B, this is usually one that is commonly missed when I teach this in my seated class. They want us to approximate the number of iPods sold during the third quarter of 2008. So if you look at 2008 and your third quarter is this green wedge here, visually, it looks like that wedge is underneath 10. And so a most common wrong answer folks will give me is say, oh, well, 9 million. However, if you'll notice, this graph is broken up into blocks. Likewise, these individual stacks here are also in blocks. So each of these blocks would represent 5 million. So here you have 5 million and then another 5 million. So there's 10 million. You're already over 10 million. Even though visually the graph looks like it's under the 10, it's a distortion there, as I mentioned, is a common disadvantage. And then you've got a tad just above that 10 million there. So I would say here then it's approximately 12 million. You have to, in this particular example, it has to be something over 10 million. So probably a good range then would be somewhere between 12 to 13 million as far as a final answer there. Okay, so I just wanted to address that. And then I'm going to scoot on over to the next page. Probably one of the most cutting edge, newest type graphs that are becoming quite prevalent in this day and time are infographics, and I've started seeing them a lot more since I've been teaching this class. I guess I just didn't have my eyes sort of tuned to being able to see them, but I've seen them, not looking for them, just seeing them on the fly. So the infographic that you'll see on your book on page 341 is in reference to college being a valuable experience. And the point of an infographic is that you can provide a wealth of information, statistics that have been studied, and you can provide that all in one spot. The disadvantage is that there's a lot going on a particular infographic, but it combines percentages, text, as well as graphics to sort of help convey an overall message. So, for example, in part A, it says, well, what percentage of students feel that their coursework is relevant to their lives? When you first look at that, this question here, there's a lot to look at on this page to find out that one specific piece of information there. But it's actually right at the top of the page on page 341. It's the second sentence. It says 58% of students feel that their coursework is relevant to their everyday lives. And then in part B, I sort of did a throwback back to Unit 1 just to sort of make sure we don't forget what we don't want to forget our roots. So in part B, it says, well, if 1,000 students were surveyed, how many would have texted in class according to this infographic? So even if you can't find, like the word texting in class, hopefully your eye would be drawn to what looks like a text, which is a picture there on the graph. It's over about midway of the page on the right, and you'll see that 79% of students say that they have texted in class. Well, remember, this problem is not asking what percent, it's asking how many students. So we're saying then I want to figure out what 79% of my 1,000 students are. So hopefully you recall our formula from last unit, part equals percent times whole. And so with that said, our percentage, 79%, will go in the percent spot. We got to change it to a decimal, so 0.79. Divide it by 100 or move that decimal 2 places to the left. That 1,000 students, that's our total number of students, so we're going to put that in the whole spot, and we don't know what part. And then from this point, you can just throw that in your calculator. 0.79 times 1,000 will give you 790. So 790 students then out of that 1,000 would have said that they had texted during class while in college, for example. Okay. And then we'll close up shop here in section 5D, which will be focused on some common characteristics of misleading graphs. And so the first one that I'll look at here are perceptual distortions. So if you look at in 1980, they have the standard dollar bill. And then 10 years later, in 1990, they have the standard dollar bill as well. But they're saying that in 1980, a dollar bill was truly worth $1. But by 1990, the dollar bill was worth 63 cents. And then if you go down to 2005, they say that the dollar bill was worth 42 cents. If you look at this bottom bill here and ask yourself, how many of these could you fit in that top graphic? I don't know about you, but to me, it looks like I could probably fit 4 of these in that top graphic. Well, if I could fit 4 of these in that top graphic, then that means that really this shouldn't be 42 cents. This should have been 25 cents. So it's not that their math here is wrong at all. It's the distortion of the graph itself. What they have not only done, that your eye is drawn to the fact that not only the length of this dollar bill is changing, but also the width, making the overall area of that dollar bill change. So unfortunately, if they wanted to keep this a true representation, what they should have done is that they should have, let me erase that, not changed the width at all on any of these dollar bills and kept the width the same and only changed the length. If they had only changed the length, then we wouldn't have that ability to say, oh, well, if I can fit 4 of these in there, then this really should be representing a quarter. Okay, so that was the idea there. In next page, you always want to watch the scale of your x and y axis. And on all actuality here, in number 2 here, this is the exact same data set. However, the graph on the left makes it appear that women as college students took a large, drastic spike from 1950 through 2000. However, the graph on the right, the exact same data, you can see that while there was in 1950 a gradual increase, it wasn't near the drastic spike that we see over here on the left. And all that has to do with the fact is that if you look at the scaling, over on the left graph, they started the y-axis at 30 versus over on the right, starting that y-axis at 0 makes such a huge difference. So that uniform scaling, it is uniform on both sides. However, not starting at 0 made this appear, it's kind of like you zoomed in on the graph and made that appear more drastic than it actually is, because in all actuality, it's over here, it's the same data set, it's a very gradual increase. If we scoot on down then, the next one that I'll draw your attention to is graphs that can show a percent change, and you can find that in your textbook on page 344, and they are looking at public versus private institutions, and while it appears that the cost of public education has fallen, it's really showing that the costs have just risen by smaller amounts. It can be very misleading. So you have to make sure that you're asking yourself, because it kind of makes it look like, oh, that public education is falling. But really what it means is that the difference between those costs are just rising by smaller amounts, okay? And then lastly are pictographs. Not all pictographs are misleading. This one happens to be, though. Sometimes it's just the introduction of a piece of artwork, kind of like you saw with the visual distortion with the dollar bill a minute ago. Adding that picture, sometimes they don't think it all the way through. And so with this pictograph, it's trying to represent the world population in billions of people. And so what they're showing is that from 1804 to 1927, which is a difference of 123 years, In 123 years, the population has increased by 1 billion. However, the next set of years from 1927 to 1960, that's only representing 33 years, it's increased by another billion. And then it takes 14 years for it to increase by another billion. And then I'll do this one more time. It's increasing by 13 years from 74 to 87. That's 13 years. It takes it to increase another billion. The only way for this to truly be accurate is that this x-axis down here to be truly increasing by 1 billion every so often, it needs to be, what they're trying to show is that this is uniform, and it is not uniform by any stretch of the imagination, because it took 123 years, then it took 33, then it took 14, then it took 13 to increase by 1 billion. So that horizontal axis is not uniform in size, which makes for a misleading graph here, because it is not rising at a linear rate, okay? All right, so hopefully this has been informative for you for more intricate graphs. Thanks a lot.